everyone. I'm Yehlin, and for the mini session, I'm gonna briefly talk about the Bindcraft, which is the one-shot design of the functional protein binders. So Bindcraft is using AlphaFold model instead of Rosetta fold model, and it is not retrained version using a diffusion techniques. It's just solely using an AlphaFold, but in a hallucination way. So briefly talking about the designs, binder designs before deep learning, people try to use a lot of physics-based method or segment-based method to try to make it binders or make some permutation to increase the a binding affinity toward the target. And the whole process, usually it takes thousands of different proteins in silico and filtering them out using an in silico way, and testing 1,000 to 10,000 proteins and experimentally get few binders, which have a very low success rate. But once AlphaFold came out, people tried to use this AlphaFold model to actually design or filtering out the binders, and it actually really works well because AlphaFold has its own confidence score PLDT or PAE, which can give you the insight about the interaction between two different target and a binder, and you can actually use this kind of confidence score to filter out your designs, and it really achieves a high success rate. So the Bindcraft whole process is using the AlphaFold 2 model, and the binding target could be very difficult. It have a more aloof region or very small hydrophobic patch, or it's can be an undruggable target. So there are many reasons that the targets can be very difficult. But I think the AlphaFold models are it's available to design something de novo proteins that. Actually, you can just design 1,000 of different designs and filter out based on the PAE value or PLDT value, and it helps to find the binder with a very high specificity and high binding affinity. But I'm not so sure about why those binding targets are previously difficult but now available. Okay, so this is the architecture of the AlphaFold 2 model. So it gets a sequence and MSA as an input, and it generate a profile of it and input into the MSA module, which is the EVA former of the AlphaFold. And throughout the structure model and throughout the multiple recycling steps, it refines the structure more and more, and finally it gets some structure with the confidence levels. So what does AlphaFold actually return as given a sequence MSA or template as an input? Throughout the MSA module, it output the histogram, which is the distance probability of the pairwise residues. And after the structure module, with the predicted structure, it predicts the site-wise and the pairwise confidence, which is the PLDT and the PA score or PDE score in this cases. So what does PLDT tell? PLDT is a local confidence per position, so it has a range from 0 to 100. So usually the higher is better. So higher score, if you have more than 70 score, is usually regarded as a confident region. But if you have less than 70, it's usually regarded as a not confident region. It works for monomer, but also works as well for the multimals, and then. The PAE score as a confidence for every pair of positions. So if you have a length of L protein sequence, it outputs the L by L matrix, which investigates all the pair of residues confidence. So for typically for the multimals, you can focus on the interchange residue, which is the red part here. So if your proteins are not really binding well or having a high uncertainty at the interface, it will outputting the high score for the PAE. So people usually filter out the binder whether it bind or not based on the PA score, for example, PA with the 15. And PTM is something similar to PAE, but it's an integrated version of the PAE. So it predicts the value range from 0 to 1, and people filter out based on PTM score. If your PTM score is larger than 0.6, it's usually regarded as a confidence structure. So so this is actually a structure prediction model, not the designing tool. But can we actually use this model for the designing purposes? So the really cool thing about the AlphaFold is like for the de novo protein, which doesn't have any MSA information, evolutionary information, it can just predict the structure with a one single sequence, right? You can just give a one single sequence information to the MSA and construct a profile and input into MSA, and you can get the very highly confident structure for the de novo sequence. So all you need for de novo protein design is just a single sequence information. And to design the protein, you actually need to you actually need something for you to optimize. For example, if you input a really random bad sequence, the model will not think this sequence will be confident. So the confidence level will be super low. But if you input the model with very high confidence, the model will outputting a structure with a very high confidence. So yeah, the models already know which sequence is bad and which sequence is good. So based on the sequence information you input, the model can correctly predict the confidence level. So to design a protein, all you need are just loss and confidence matrices. So starting from the random sequence, you make the model to predict something, and you get the loss confidence score and make it as a loss function and backpropagate through this model through the gradient optimization and update the sequence, not the model itself. So you're accumulating the gradient from the sequence, input sequence to the output loss and backpropagate that loss into the original sequence and redo this process until your loss is going down and down and down. So until you really get some structure with a very high confidence. So this is real cool because you don't need to train the model, and all you need is you need to set your loss or confidence matrices. And the other really cool thing about the AlphaFold is it's really hard to actually backpropagate the sequence if you use the one-hot encoded sequences, right? Because you need to make each single position to be 1 if you choose that amino acid, but you need to set the position of that amino acid to be 0 if you're not going to choose that amino acid. So if you backpropagate through the one-hot encoded losses, it will be very unstable because if you change several positions together, it will completely predict this different structure and the loss will be fluctuated. But the AlphaFold works really well with the soft lossed input. So if you give this soft lossed to this AlphaFold module, it will still predict some losses, and you can optimize through this soft losses piece. So the way Bindcraft optimize these losses is it started with a soft losses and it applied a softmax. So if you sum the 20 amino acid probability at each single position, it will be sum equal to 1, and you input the soft max losses into the AlphaFold and predict some structure and backpropagate until you get a really low loss. So also some trick they use is they normalize the gradient, gradients. So here in this case, you can prevent the model to be suffered by very small amount of the gradient or very large amount of the gradient. So prevent your model to be really unstable. And you can also modulate the learning rate in this case. So you can multiply the learning rate with the gradient you calculated throughout this model, and you can extract that from the original losses to update the loss into the next step. So yeah, actually the Bindcraft was not first application using this hallucination technique. So this paper 3 years ago, Christopher Norn applied this hallucination technique on tier Rosetta. So tier Rosetta is something similar to AlphaFold. It's get sequences of input but predict the 60 features angles and the 2D distance matrix as an output, and it reveals the 3D structure using a Rosetta. So the way they use the hallucination technique is they have specific target they want to design, and they started with a random amino acid sequence. So you make your model to predict the structure and optimize the loss between the predicted structure and the target structure, and try to minimize the loss and get the sequence that can be actually folded into your target structure. And this is the second application using AlphaFold 2 is also like generating the sequence for your desirable like structure here. So in this case, they also use a gradient optimization, but MCMC optimization, which is like making a single mutation and you decide whether to accept or reject based on your loss function. So if your loss function is going up, you want to reject the mutation, but if your loss function is going down, you want to accept the mutation. So it's a combination of gradient optimization and the MCMC optimization. So yeah, so after that, like now we have this tool called Bindcraft, designing the binder given a target. So it's not a like fixed backbone binder design, but given a target, we give the freedom to the binder and let the binder to just bind to our like fixed backbone target. So it started with the AlphaFold 2 Mulitmer model, and it like randomly hallucinated like on the surface, or you can also give a hotspot of the target protein, so like make the specific binder to bind to that hotspot. So the first step is actually using this AlphaFold 2 Mulitmer model to generating the binders. So yeah, the difference like with the Rosetta fold like diffusion model, the AlphaFold model is simultaneously generating the sequence and the structure together. Since this is a like structure prediction model, you need sequence to predict the structure, and yeah, and you're like optimizing your sequence through the structure. So you're always like getting a pair of sequence and the structure together, not a like sequencer step like generating the structure first and redesigning with the MPNN. And, like anyway, later like we can redesign with the MPNN, but the cool thing is this model like can predict something based on both structure and the sequence together. And is the first part of this hallucination is composed of these 4 stages. It looks complicated, but one like common thing of this whole process is like you start with a very, very soft losses, make it into be more like one-hot encoded, which is like more fixed amino acid losses. So you start with the soft to make into more like fixed amino acid sequence. So the reason they designed this whole pipeline like this is if you hallucinate throughout the one-hot encoded sequence space, the model like easily gets really unstable. So they wanted to prevent it. So like give as much as freedom at the first like few stages by like running it through the soft losses space and the soft max stage, and like make the things to be one-hot encoded, and like after that make some mutations to really optimize the structure and sequence. So like for the first steps, it's really started, the first stage is like starting from the losses, it changed the losses smoothly to the softmax sequence. So you can see that the number of steps, each iteration, we multiply with the lambda, which is the step divided by the iterations. So if the lambda is 0 at the first stage, so you completely hallucinated through the losses. But if lambda like goes higher and like at the certain stage, it will like be equal to 1, and it means like you will run the hallucination process with the softmax losses. So it goes from the losses to the softmax. And then from the second stage, you started with the like very high temperature, which is like more generating more uniformly distributed amino acid losses, but you want to like change from softmax to the one-hot encoded version, which is like you can decreasing the temperature. So for example, like decreasing the temperature from 1 to 0.1 to make the amino acid distribution to be more sharp. So in that case, like yeah, you starting from more relaxed version of the sequence and like making it to be more sharper. So the third stage is one-hot encoded stage. So you still backpropagated through the softmax representation by adding the softmax representation and like extracting the softmax representation to the one-hot encoded representation. So you can still backpropagate through this, but like the actual input to the model itself is like one-hot encoded sequence. And then the last step is like given that binary sequence, you just like make a random amino acid mutation based on the losses you get from the one-hot encoded sequence, and then like make some search random search and like accept if the loss is going down, but like reject if the loss is going up. So in this final stage, you're just optimizing your sequence more and more. So the whole process looks like this. So the really cool thing about this is like, yeah, it actually really designed a lot of diverse structures and like either like alpha helix, but also the beta sheaths and the like combination of the alpha helix and the beta sheath structure. And also the really cool thing is you can actually modulate the loss functions to bias your final structure to be like have more beta sheaths or like more alpha helix like this. So for example, they implemented the negative loss function for the helix. So if you want to like prevent your model to generating just a helical structure, you can just maximize the loss. And then depending like how the helicity weight, as you can see in this like box plot, you can see that the percentage of the beta sheet is going up as you increasing the helicity weight, right? So if you really want to like design this sheet structure, you can just like upweighting the helicity weight. And yeah, so throughout the first hallucination part, you can like get the candidates of like binder, and after that, maybe like it's better to filter them out based on the confidence score, like PLDT and the number of contacts, because like in many cases, when you design a binder, there are like some cases you design something have a high, like a low inter-PA score and high PLDT, but like sometimes they have a lot of like unsaturated polar residue that doesn't like make any hydrogen bond with the like residue on the target. But if you have that kind of like unsaturated residue, is very energetically unfavorable. So it's better to avoid that situation. So the way people usually filter out is like filter out very low PLDT score and like also filter out the binders that have very few contacts and like, yes, very significant or significant backbone clashes are rejected. So the second process is like although you can get this binder structure and the sequence all together throughout this hallucination process, you can still like redesign with the MPNN, because MPNN is a like tool that can design something really solubilized, and the tools that can like generate the sequences like could be more expressed really well in a real like environment. So yeah, there are a lot of like approaches. People design the backbone and then like redesign something with the MPNN again. So here we also apply the same approach. So, but the interesting thing here is we didn't change the interface sequence. So like given a fixed interface sequence, we designed the rest part of it, like because we think our AlphaFold is already like optimized the interface residue interactions. So we wanted to like not to make the ProteinMPNN to redesign the interface residues. So here, preserve the binding residue and then redesign with the 20 new sequences for the remaining binder, and then like using a soluble MPNN with a temperature of 0.1 and then like 0.0 backbone noise. Yep, so the final part is after you redesign with the MPNN, repredict it back with the AlphaFold 2 model to make sure whether your binder bind well to the target structure. But here in this case, instead of like using an AlphaFold 2 multimode model, we use the AlphaFold 2 monomer model. The reason behind this is like AlphaFold 2 monomer model is exclusively trained on the monomeric proteins. So like we thought, oh, maybe we can decrease the bias, like regarding of like protein-protein interactions coming out from the AlphaFold 2 multimode model. So in that case, we can really robustly filtering out the high-quality interfaces. So yep, here we use the AlphaFold 2 monomer model for the finer filtering, and then after that, we relax with the Rosetta, and then like get the energy terms and the number of like unsaturated hydrogen bonds and like saturated hydrogen bonds, and like try to filter out based on that kind of like different factors. So after that, in this paper, they really investigated a lot of like different targets, like that's also like membrane targets and targets with a loop region, small like hydropatch patch region, and like they really got a like good binders with a very low, very high affinity. Yep. So this is all about the Bindcraft, and I think it's really cool tools because like you can co-optimize the sequence and the structure all together. So it's like kind of like chain of thoughts. So you let model to think about like what kind of like structure is like confident with this sequence, like and make the model itself like to fix their sequence and structure simultaneously together. So yes, like, but the one limitation coming out from that is it takes a long running time. So you usually like require a large GPU memory requirements, and like imagine you want to generate a very large binder, like the computation time is like correlated with the length of the protein. So yeah, you will like suffered by the running time issue. And then not like so far, like there are like a huge success rate for very different kind of targets, but not all the target sites are like acceptable, because when you want to like design some binder to the membrane protein, you want to like make your binder to be like purposely just specifically bind to the region which is like outside of the membrane, like not in the membrane. But now like if you design on some membrane proteins, it's sometimes like bind to the membrane region or like the top region which is the outside of the membrane region. So yeah, maybe like for the next version, like we need like more strict masking techniques to mask out the regions we really want to prevent the binder to be bind to. And lastly, protein with the like entirely hydrophilic surface, in that case, like model is like still have a hard time to finding a good good binders. Yep. They didn't really try with the smaller proteins, but theoretically it should work but the one concern is like sometimes AlphaFold is not really confident with the like small peptide because like they have a lot of like flexibility. So if the model itself like does not really predict the right binding mode, like we can't really trust the designs, right? So the reason they fix the length within a range of like 60 to like 150 is like to make sure at least the model like can predict something confident.